It's the question of present climate change, the rate of climate change, and I've got a polar perspective on it, but I'm going to try and not stress that, but stress what is happening to the global climate as a whole and how fast it's happening, and then what we can try to do to mitigate this, and what effects are going to be happening when. So this is a well-known curve called the hockey stick curve that was produced by Mann and Bradley, which is the climate record for the past 1,000 years, and this comes from coals, crystal cone pines, thermometers, and ice cores. Every possible type of analysis was done, and what we know is that the climate's been getting gradually cooler because the history of ice ages is that we come quickly out of an ice age and then we gradually, slowly descend towards the next one. And this is a very slow process, and it takes a few thousand years to tens of thousands of years until we start to get glaciation occurring again, and the world sinks towards the next ice age. So very gradually the climate's been getting cooler, but only by about 0.2 or 0.3 of a degree since the year 1000. But there's some disagreement about this curve, and in certain parts of the world there have been more rapid changes that emphasise the fact that it got quite rapidly cooler around about the 14th, 15th century, and we had a period called the Little Ice Age, from which we started to recover with coming of industrialisation, and that in certain areas like the Northern Hemisphere it was quite distinctly warmer about 1,000 years ago, hence the colonisation of Greenland. So this is a global average, but showing a slow descent. But then suddenly something happened about here, about 1850, the Industrial Revolution happened, and we started to pump carbon dioxide into the atmosphere from burning coal, and the temperature rose very rapidly. And this coincided with foundation of meteorological offices, so the thermometer record became good, and so we know very well how fast this happened. So if we look at the expansion of this last 150 years, we see that we had a warming during the late 19th century, which brought us up to quite a warm temperature around about 1940. Then there was a pause for about 40 years, and then it started to rise rapidly again. Now the pause is thought to have been due to a big increase in the use of coal, especially poor quality coal in power stations and factories, and that coal produced a lot of smoke, and the smoke actually reduced the rate of warming by reduced by absorption in some of the solar radiation. So according to the modelers anyway, they can explain why warming paused from 1940 to 1980 in terms of the increased use of coal, and then we started to clean up our act with coal, and global warming took off again. So we've had about 0.8 of a degree of warming since the late 19th century until today, globally. Now that's globally, but it's different in different parts of the world. And one of the places where it's most rapid is the Arctic. And warming in the Arctic is about 2 to 3 times as rapid as in the rest of the world. And this is a process called Arctic amplification. There's various reasons for it connected with the troposphere in the Arctic that being thinner than in other latitudes. But it's getting larger, the ratio is getting larger, because as the sea ice retreats in the Arctic, we're getting an increased warming there because of increased absorption of radiation. So the ratio itself is rising. And we can see that because if we look at the past 150 years, this is what the planet's been doing with a warming of about 0.8 of a degree. If we look at just stations north of 60 degrees, we find the same shape, a warming, a pause, and then a warming again. But instead of being 0.8 of a degree, we're getting something like 3 degrees of change. So the Arctic has reproduced what the world is doing, but with a big magnification of a factor of at least 3 here. So we've seen this Arctic amplification effect. And this means that everything that's happening in the world is happening faster in the Arctic, or happening first in the Arctic. So the Arctic tells us what's going to be happening to the rest of us. And we can see this is looking at the amount of warming that's happened since the 1950s, and as a function of latitude. And we can see that when we get into high northern latitudes, we get this big amplification factor of 2, 3, even 4 times as you get towards high northern latitudes compared to lower rates of warming in the rest of the world. If we look at the Arctic and see how fast the warming's happening over the last 20 or 30 years, it's been biggest, the greatest amount of warming has been in the Arctic Ocean, around the edges of the Arctic Ocean, and Baffin Bay and the Greenland Sea. Those are oceans where the sea ice has been retreating in recent years, so that we have open water in summer, whereas previously we had ice there, and that's equivalent to a large amount of extra warming. So this western part of the Arctic, for instance, north of Alaska and Siberia, is ice-free in summer now, and never used to be, so that gives us this greatly increased warming rate. But we can see there's a warming rate around the whole Arctic, including the tundra regions and the Greenland ice sheet. Now, the people who don't believe in global warming have said, well, we don't believe in global warming because there hasn't been any warming of the planet since 1998. And they'll point to this curve, which shows the global average temperature. And it did hit a high in 1998. And if you just look at 1998 versus subsequent years, you can say, well, there hasn't been any more warming. But you can see that the trend is up, continues to be upwards. And also, if you look at how the warming is related to latitude, we can see that there's continued to be warming in the high northern latitudes. So the Arctic, this is the dark colour here is maximum warming rate, 2 to 3 degrees, is still continuing in high northern latitudes, even if it's not continuing in other latitudes. So the amount of global heating has continued, and in fact, the amount of heat we're putting into the atmosphere has continued to increase because CO2 levels in the atmosphere continue to rise exponentially, and that involves putting heat into the atmosphere, and it's just a lot of it is disappearing somewhere, and somewhere seems to be into the deep ocean. But it's disappearing into deep ocean, but at some point it's going to emerge from the deep ocean, and we'll get a rapidly increasing warming again. So if we look at what the models predict for how much warming there's going to be, this is the last IPCC projections, and there's 3 projections shown here. The middle one is business as usual. Business as usual means continuing to increase our emissions from fossil fuels in about the rate we're increasing them now, and this will give us, by the end of the century, and this is predicting for the end of, this is 2020s, this is the end of the century, we can see we're going to be getting warming of about 4 degrees over most of the planet's land surfaces. But because of Arctic amplification, we'll be getting 6 to 7 degrees in the Arctic. That's the purple colour here. So that's quite a major warming of the Arctic, but it's also a major warming of the rest of the planet. 4 degrees is not something that the planet can cope with very well. If this is what's happening, if we have a continued increase in the rates of emissions, and we don't do anything at all to slow them down, this is a high emission scenario, and here we can get 8 degrees of warming in the polar regions and more than 4 degrees in the rest of the world. This is an impossible to achieve scenario, which IPCC likes to show, but they know that they don't tell you that this can't be achieved without actually removing carbon dioxide from the atmosphere. So we have to find ways of taking CO2 out of the atmosphere in order to achieve this low rate of increase, and this will still give us about 2 to 3 degrees of warming by the end of the century in most latitudes, and 4 degrees plus in the Arctic. So this is pretty frightening. But if we look at the amount of warming that's happened in the past, we can see that things are even more frightening. And this is the ice core record from Antarctica of the climate of the past, from oxygen isotope ratios, and from analysis of tiny air bubbles in the ice cores, which gives you the carbon dioxide content. So the temperature shows this kind of seesaw where we've had what we typically have, this is going backwards in time here, you come quickly out of an ice age, then you go slowly back towards the next ice age, and that takes about 100,000 years or so, and then this is the last ice age we came out of, which was we came out of it about 12,000 BC. We came again very quickly out of it, except for a little jog called the Younger Dryas, which was a little event where we went back towards an ice age. We came out, and we've been sitting here ever since, and this is the whole of recorded history. That's about the last 10,000 years. We had a relatively stable climate, we invented agriculture, we invented civilization, everything was done. Man was around right through this period, at least something resembling man was around, but he wasn't affecting the planet at all until this last little period here where we started to have agriculture and then industry. So this is where we've been affecting the planet. But you can see that we've actually been quite lucky, because we've had about 10,000 years of very steady climate of a post-interglacial warm period, whereas the last ice age, we came out of it and immediately started to cool towards the next one, and the one before that as well, and the one before that. So we're actually lucky at the moment that we haven't gone towards the next ice age. But you can see this sort of sawtooth, a slow descent and a rapid emergence. And the same is shown in the carbon dioxide levels, which of course, when you have a warmer climate, you have more growth of plants, and so you have higher carbon dioxide levels. And so you've got, this is the dust level found in ice cores, and you can see that the dust levels seem to be highest when you're at the depth of a glaciation. So there was a high dust level here and a high dust level before we came out of the last ice age. That's because when you've got when water is locked up in ice sheets, sea level is much lower, so there's a lot of continental shelf which is actually dry land, and so where you have a bigger area of literally dry land, so you have more dust emissions. So this is indicating drying out due to water locked up in ice sheets. But anyway, you can see this basic correspondence between CO2 and temperature, and it's tempting, and it's so simple that one wonders why people haven't done it, is that you can say, what's the natural correlation between CO2 and temperature? In other words, if you have a certain rise in CO2, what rise in temperature does that correspond to? So we can come to a natural sort of doubling rate, which is how much warming would the Earth have if we double the CO2 level, and that's the climate sensitivity of the Earth. We're taking it to be somewhere between 2 and 4 degrees in all the calculations that we do. But if you took this and looked at ice ages, you get something like 8 degrees. So what that means is that if you increase CO2 levels, the ultimate warming that the planet will have is a lot more than we've actually had. There's a rapid warming, which is what happens as a response to CO2. There's a slower warming, which is what happens if we, say, hold CO2 levels steady and we still get some continued warming. And then there's the ultimate warming. If we hold CO2 levels steady forever, we'll end up still with a lot of warming, but it will gradually asymptotically reach that limit. And that limit seems to be sort of 8 degrees for doubling, which is a lot. So this is what we learn from ice cores, and also we learn that the natural tendency of the planet is to go between about 180 and 280 as the CO2 level in the depths of an ice age and the CO2 level during an interglacial. Those are the sort of nature's preferred CO2 levels for the planet in parts per million. So in fact, when we came out of the last ice age, we were at 270 parts per million, and we stayed at there right until 1850. And so we, right from the year dot, well, the year 10,000 BC until 1850, we were at about 280 parts per thousand. Suddenly, parts per million rather, suddenly we started putting carbon dioxide into the atmosphere, and you see how rapidly the CO2 content of the atmosphere rose. Also the methane content of the atmosphere and the nitrous oxide content, everything that's to do with things that man has done. And so this is a massive experiment we've been doing with the planet. This is what the planet likes to have as its CO2 level. We've given it that much extra. It's gone up to 400 now, which means it's now 50%, 40 to 50% above what the planet would like to be at. So we are really abusing the planet, and we're conducting a global experiment. The trouble is we've only got one planet to conduct it on, so we can't go to another planet if this one experiment failed. And when we look at where those emissions are coming from, we in Europe feel all good, and the US feels good because our emissions have been going down. This is the Europe as a whole, and this is the EU. In recent years that's been going down, but the only reason it's been going down is because China's been going up. In other words, we've passed all our dirty manufacturing over to China, and they make things in a very inefficient way with factories powered by electricity generated by coal-fired power stations. So all the filthy climate change producing effects are in China, and we can feel virtuous because we're going down, but that's only because China's going up, and also India. But as a whole, the world is rising exponentially in its CO2 emissions, and one of the worst offending substances is cement, which maybe not, people aren't fully aware how evil cement is, because it's not only do you need a lot of energy to produce cement, but the chemical process by which cement is produced itself produces CO2. So you're using energy to make cement, and then the cement making process itself chemically produces CO2. So cement is really evil. I mean, you should never make buildings out of concrete. You should make buildings out of wood and glass and anything but concrete. But unfortunately, China is the world's greatest concrete manufacturer, and there's a state monopoly of cement, so there's no incentive not to produce massive amounts of concrete. So when you go to China, you see concrete buildings everywhere. So this is all bad news. When we look at all these substances we're putting into the atmosphere, we can express the effect on the climate by the amount of radiative forcing. Radiative forcing is just, we imagine that we're keeping the amount of radiation from the sun the same, which we are, but we're adding these substances to the atmosphere which are absorbing outgoing radiation. Absorbing some of the long-wave outgoing radiation is equivalent to keeping the outgoing radiation the same, but letting more shortwave radiation in. So we can compare, so the radiative forcing is really trying to compare, it's simply the climatic effect of the different additives to the atmosphere. And we see that CO2 is the biggest offender, but methane is actually catching up quite fast. It's about a third as much as the CO2 effect. There's an effect from ozone still, and there's an effect still from halocarbons, which when we had the Montreal Protocol on CFCs to prevent the ozone hole from happening, they insisted that you should use a different form of halocarbon, then this wouldn't produce an ozone hole. Unfortunately, the halocarbon that's now allowed is actually a very powerful greenhouse gas. So we've got this yellow bit, which is, we've got rid of the ozone hole, but we've added to global warming. And then there's, these are the aerosols of gunk that we put into the atmosphere, so which does reduce our warming a fair amount. Clouds, of course, also reduce the warming. So you add all these lot together and you get this amount of radiative forcing, which is roughly the same as carbon dioxide alone. So if you take all these negative effects, they're offset by the methane. And so the radiative forcing is about 1.6 watts per square metre, and the amount of radiation we get from the sun on average is about 400 watts per square metre. So man is adding about 0.5% to the solar radiation, and that's enough to do all these things to the climate. So that's what's going on to the planet as a whole, and the fact that the Arctic's warming faster than other parts of the world shows has certain impacts that are global and not just local. So that I've listed 7 here, so I'll just run quickly through them. Firstly, the sea ice retreats, which is what I work on, and that gives you a feedback which increases the planetary albedo, or decreases the planetary albedo rather, means more radiation is absorbed by the planet instead of being reflected, and that causes an acceleration of the retreat. Then the warming of the retreat of the sea ice causes the Greenland ice sheet to melt faster, and that causes global sea level rise to increase. The snow line also retreats because it's warmer, and that has another albedo feedback. There's a specific threat from methane, which I'll talk about a bit later, and the whole thing has an impact on food production via a linkage with extreme weather events. And there's also a decline in the Atlantic thermohaline circulation, which actually has a cooling effect on Britain anyway. So there's one I left so the good bit for Britain is right at the end, so at least we've got something good happening for us. So firstly, the sea ice retreat. The Arctic sea ice was started to be seen to be retreating about 1950, but only in summer. In the winter, the Arctic sea ice the whole Arctic Ocean is frozen right up to all the land masses around it. So even if the Arctic wanted to retreat, it couldn't. So in all the other seasons of the year, it took a long while for any retreat to show itself. But in the summer, when the Arctic gets unglued, the ice gets unglued from the coastline and starts to shrink into the middle, then you started to see a retreat about 1950, and it's been going on ever since. And it started to notice in 2005, when normally all the years that in the summer when you went to the Arctic, that the ice was still nearly all the way up to the coast. And I first went up to the Arctic in 1970, and we were going through the Northwest Passage, around through Alaska and the north of Canada, and we had a lot of trouble getting through the ice. But then by 2005 it had shrunk back, so the pink line was what it used to be, still really almost up to the coast, and in 2005 it retreated to the point where you could really see that there was open water around the Arctic in summer, and you could sail through the Northern Sea Route, North of Alaska, or the Northwest Passage. Things had changed. Then in 2007 there was a much bigger change. Somebody took a great big bite out of the Arctic, and the August and September ice retreated to the point where you really had a sea, you had an ocean, half an ocean anyway, of ice-free water, which never had happened before. The pink line was what was the case right up until 2005. This was 2007, so a huge decrease in area. Then 2012 was the next big jump down. This was the 2007 limit, the yellow, and 2012 is the white, and so it lay even further back, and it was distributed more widely, the retreat. So 2012 is so far the record. This year, 2015, it was slightly greater than 2012, but this year was the fourth smallest area in summer. And in 2012, it could have gone further. This is mid-September was when the ice reached its minimum and then started to advance. And this is a satellite picture taken on that day, and the green and yellow show reduced ice concentrations. So the ice area was all set to melt back further, and then there was a freezing spell and it started to advance again. So there could have been an even bigger retreat if the onset of winter had just delayed itself by a couple more days. What you see when that happens, of course, is the ice disappears, and it disappears via melting, and you get this kind of Swiss cheese pattern where the ice is thinning everywhere, and it melts all the way through in certain places to produce melt ponds where there's open water, and that's absorbing a lot of solar radiation. And also this is looking up from underneath. You see plenty of light because it's summer, but the ice is thin or completely gone. So you've got much more light, so you're getting a lot more plankton growth. So this is the area. The red is what's actually happened up to 2012 here, and all these wiggly lines are computer models, climate models, and we can see climate models are really inadequate, and they're not actually predicting what's happening in the Arctic at all properly. The black is the average of all the climate models used by IPCC. That's these 12 here, and you can see that reality detached itself from the modelers around about 1970 and has got further away ever since. At least it's now two standard deviations away. So the actual ice area is now less than even the most extreme predictions of climate models. So there's something wrong with climate models, although most climate models will be reluctant to admit that, but I think it's pretty clear from the data that there's something wrong there. There's processes going on which are not taken account of in climate models, and that's a dangerous thing, because that might mean the climate models are wrong for other parts of the world as well. This decrease in sea ice area, which is all of this area here, was calculated to be equivalent to adding 25% to the greenhouse gas forcing. So the direct forcing of the planet by adding greenhouse gases causes warming, insofar as that forcing causes the sea ice to retreat, and then the open water area absorbs more solar radiation. That's equivalent to adding to the forcing. So, and it's already equivalent to an extra quarter. So the danger here is we're getting towards a feedback which can lead to a runaway warming. So if the if the feedbacks are giving you extra warming to much more than the original forcing, you can get to the point where you don't need much forcing. You'll get the feedbacks alone will give you the warming, increased warming. It's just a bit like Jimi Hendrix's guitar. So it reached the point where he didn't actually have to touch the strings. The feedback alone produced the sound. So that might be the planet, warming might be like Jimi Hendrix's guitar. It's all feedback, and this we're a quarter. Just this process alone is going a quarter of the way there. Now, what does that do? First of all, this is what the Arctic looks like if you go around on it, and in winter, the ice is in first year ice. This is quite thin, about 1.5 meters thick, and but in the past you had something called multi-year ice, which was ice that was many years old, and most of the ice in the Arctic was many years old. So when you went around in the Arctic, it didn't look like this. It looked like massive, great ridges, hugely thick ice that you couldn't get through even in an icebreaker. But the amount of multi-year ice in the Arctic, which was the red area, has gone down in the last decade, and now there's only this is all that's left. This was last summer. There was just this little bit north of Greenland, and the rest of the ice was first year ice. So you see a completely different landscape where first of all there's plenty of open water, which never was before, and then where there is ice, it's really thin stuff, easy to break through with a ship, easy to melt. So we know that, for instance, ridges, which are where the ice is pushed up into thick ridged blocks. This is the yellow is how many you get in multi-year ice areas, and the purple is how many you get in first-year ice areas. So it's easier to get through first-year ice in a ship. So how do we know all these changes have happened? Because area is easy to measure, and this is what's made things worse, is that everybody worked from area. You can see from a satellite what's the area of sea ice, because it's white, and whatever kind of sensor you use on your satellite, passive or active microwave, it looks different from open water. But thickness you can't get from a satellite. You sort of can now. In fact, there's an instrument developed at UCL that gives it, but in the past, and until very recently, you couldn't, and the only way to get thickness was to go underneath and look upwards with an echo sounder to measure the depth of the ice below the surface, the draft. And so British and American submarines have been doing this for 40 years, and I've been doing it for 40 years myself, and it involves going out in a submarine with an upward-looking echo sounder and going around as much of the Arctic as you possibly can, measuring the thickness. And in doing this was how we first found that the thickness was going down. So, for instance, this was thicknesses I measured in 1976, and this is thicknesses in 1987, and this is thicknesses in 2004, and we can see the average has been going very much down from 5, 6, 7 meters here to 4 here and 2 now. So over the Arctic as a whole, the thickness has gone down by more than 40% over the past 30 years. So it's not just that the ice is shrinking, but the remaining ice is much thinner than it used to be. So the volume of ice in the Arctic has gone down by more than 70% in summer. And that's a huge change in the planet to have 70% less ice than you used to in the Arctic. So that's where something went. What we do now, firstly, we don't use submarines anymore because, at least in Britain, because first of all we don't have any left, and secondly they are quite dangerous. The last one I was on that I took a picture of had an accident and a couple of sailors were killed. So we now use unmanned vehicles which are safer, and so they're like, this is called AUVs, autonomous underwater vehicles, and you program them to run under the ice. They're like torpedoes, and they have upward-looking echo sounders, and they'll run under ice, but they can't cover the whole Arctic Ocean, just limited regions, and it's a lot more work. In the submarine, you just get in the submarine and sit there and measure things, but with an AUV, you have to go and set up a camp like this, and then you cut a hole in the ice, and then you can put the AUV through it. And then you can get these very nice maps of the underside of the ice and the thickness. So it gives you a nice result, but much more work per unit of data than it used to be. So we can see the ridged ice, and there's some multi-year ice with very big thick ridges, and then thinner ice, younger ice with little ridges. So we do that now, and when we put together all this British data with the US data, we find that the volume, the area was going down linearly with time, but because the ice is thinning as well, the volume is going down more than linearly, it's going down exponentially, and the volume, we look at volume, what we get is what's been called the death spiral, which is that if you look at each month of the year and you plot it on a polar graph, we can see this is the black is September, the minimum month, and you go back to 1979 and you had about 17,000 square cubic kilometres in summer, but when you go round towards today, it's spiralling in towards the middle, and there's only about less than a quarter as much ice in the summer now as there was in 1979. And every other month of the year is also showing a spiralling in towards the middle. When you get to the middle, there isn't any ice left. So September is likely to become ice-free quite soon, but other months will last longer, but eventually some of the other months of the year will spiral into the centre as well. So this is what's called the Arctic death spiral, because it's causing the death of the ice. And this is looking at September, and this is alone, and we can see it's going down, the volume is going down more than linearly, and if we project that down to zero, we get it going down to zero somewhere between 2015 and 2020. We didn't go down to zero this year, so that was so that minimum date was wrong, but it's pretty clear that despite kind of wiggles from year to year, the trend is downwards, and it will disappear in the month of September. The ice will disappear pretty soon, and it's looking like 2020 is about the most that we'll get. Still some ice in the summer. So the consequences of that, first of all, you don't want to have if you're a scientist, you used to work in the summer, in the winter from ice camps, and you'd have aircraft flying out, and you set up an ice camp with a nice safe runway, and the aircraft would fly you in and out. But now this is March of 2013, and this is the breakup of the ice that happened in March, when normally the ice is solid, and instead, now it's thin, you get all this kind of breakup, so that you would never be able to have an ice camp in the Arctic in March. And so all of the research that people have done from ice camps can't carry on, and we have to use ships now at all times of the year. So what we use now are drifting ships, so that the ship is the equivalent of the ice camp. And then the undeformed ice, the first year ice is thinner than it used to be, so that's dangerous. For instance, the Inuit hunters find there's been a lot of accidents where they've gone through the ice, which never used to be the case. This is Northwest Greenland. But, of course, some things are easier. For instance, you can get at the oil more easily. If you do oil exploration, this was Shell before they had no accident. Well, the shell withdrew from Arctic exploration this summer. I was up in the Arctic last month in an icebreaker, and when we sailed up through Bering Strait and up into the Arctic Ocean, there was the Shell drilling rig with lots of ships around it going strong. When we came back, it had disappeared because in the while we were up there, Shell decided to withdraw from Arctic exploration. So the vessel they were using, which itself had run aground the previous year, was a floating production platform, and the icebreakers used to go round and round, breaking up the ice to reduce the pressure on it. So if you have thinner ice, it's easier to do that, but of course it's still not safe. And shipping is going to increase because you've now got the Northern Sea Route, north of Alaska, north of Siberia, and the Northwest Passage, both enormously reducing the transit distance between Europe and either the west coast of America or Asia, and during the summer months, that is. And this is a sort of new designs of ice-breaking cargo ships. This one actually sails backwards because its stern is more ice strength than its bow. Then the next impact is that the fact that the ice is gone in the summer means that there's warmer air over the Arctic into autumn, and that increases the melt rate from the Greenland ice sheet. So here we see very anomalous warm temperatures in October and November. This is November of 2012, a huge anomaly. And when we look at that, the effect of that on Greenland, we find that Greenland is having much warmer temperatures in summer than it used to. This is actually degrees Fahrenheit, but it's about 5 degrees warmer Fahrenheit. That's about 3 degrees centigrade. So that's increasing the melt rate of the Greenland ice sheet. So the Greenland ice sheet used to not melt at all in the summer, except just around the edges at lower altitude. And then in 2012, for the first time, the entire ice sheet had surface melt. So melt was happening all over this ice sheet. And previously people thought, well, that doesn't matter too much because it refreezes in autumn. But in fact it doesn't, because what you have are now holes all over the ice sheet called moulin, which take the meltwater and it goes down in kind of Niagara-like falls down into the interior of the ice sheet and actually down to the bedrock, and that transports the heat from the melt of the ice sheet down into the bottom of the ice sheet and increases the flow rate of glaciers and increases the melt rate of the whole ice sheet. So the rate of loss of mass has accelerated. This is a satellite which measures gravity, and it looks at how much mass of ice there is underneath it, and this is really measuring directly the loss of ice from Greenland, and it's losing about 300 cubic kilometres a year, which is more loss than all the rest of the ice sheets on the planet put together. So this is causing now, it's the main cause of sea level rise. This is curve of sea level rise up until recently, and it was always thought that the amount of sea level rise is two factors. One is as the ocean warms up, the water becomes less dense and stands higher, and then also as glaciers melt in the Alps and Alaska and so on, that puts water into the ocean. So you get about 50% of the sea level rise from glaciers and 50% from warming. But now the Greenland ice sheet alone is contributing more than the sum of those two. So Greenland is now the main cause of global sea level rise. And so IPCC has had to revise its estimates upwards. This was its estimate in 2007, this is its estimate this year. And this is, but glaciologists actually are estimating much more than this. IPCC still estimates less than a metre of sea level rise by the end of this century, but most glaciologists are thinking about much more than a metre, and some are saying several metres. And some of the best, most respected glaciologists are saying several metres, so you have to really worry there. And the impacts that will have are, there's two major impacts. One is, of course, if the sea level rises by 1, 2, 3 metres, it actually drowns a lot of cities, like Miami will disappear pretty quickly, and Shanghai. A lot of coastal cities that are low-lying have had it. But also a lot of low-lying areas of the world, like the Bay of Bengal, eastern China, will suffer from more frequent storm surges, which will cause catastrophic effects. And you can tell that from just looking at the Gaussian curve. Like, if sea level anywhere, because of tidal effects and wind and so on, follows a Gaussian curve. But if you move them, there's one of the properties of a Gaussian which makes it feel evil, the normal distribution, is that if you move the mean, then if there's some cut-off which produces catastrophic effects, like if the sea level rises more than this amount above the mean, then it produces a storm surge which causes, you know, the flood, like the floods in Holland and Britain in 1953. So that's the probability of the catastrophic effect. If you move the mean, the probability of the catastrophic effect goes up disproportionately. So you think a small change in the mean sea level isn't a big deal, but it's not a small change as far as probabilities of flooding are concerned. The probability of floods and storm surges goes up disproportionately more than the change in the mean. So you're going to have much more catastrophic floods in the Bay of Bengal and China and the North Sea. Then another sneaky thing there about this albedo effect is that as the climate warms, there's less snow in winter, and this is an anomaly. In 2012, there was this much area that normally is snow covered in June, which became snow-free. So making an area snow-free is the same as making an area ice-free. You're replacing the sea ice, you're replacing the sea ice, which is white, by open water, which is low albedo. And similarly, you replace snow by tundra or forest. It's reducing albedo from 80% to 10%. So it's as bad. And this is what's happened to the Northern Hemisphere snow cover in the last few decades. It's gone right down. We've got about a 6 million square kilometre anomaly. And that in itself doubles. I showed this effect that the sea ice retreat is like adding a quarter to global warming. This is like adding another quarter. So the feedbacks are now adding a half to the global warming produced by the gases alone. So I just repeated that other curve, that they were being complacent in saying that we're adding a quarter to greenhouse gas forcing. That's only the sea ice. When you include the snow, it's another quarter, so you're adding half. Then even more gloomy is this methane threat, which I've been working on, but most of the measurements have been done by a Russian group and published in Nature. What they do is go up each year to the shallow water of the Siberian Arctic. So the Arctic Ocean is a very strange ocean because it's mostly the centre part, the deep ocean is 4,000 to 5,000 metres deep, like the rest of the world ocean, but it's got the world's widest continental shelves, and these continental shelves are only 50 to 100 metres deep, very, very, very shallow. And the East Siberian Sea is one of those. So they've been working in the East Siberian Sea and finding huge plumes of methane coming out of the seabed in the summer. And they saw that in the East Siberian Sea, and then last year there was work done in the Laptev Sea and the Kara Sea by other groups, and they found the same thing going on in those seas as well. So everywhere there's shallow water, there seems to be methane erupting from the seabed. So why does this happen? Well, the reason is that in the past, in the summer, the sea ice was right up against the coast, and so long as there was ice there, the water underneath it was at 0 degrees or below 0 degrees, so there was no warming of the seawater. But as soon as the sea ice is allowed to retreat, the seawater can warm up, and you've got a lot of solar radiation in summer, you've got shallow water, so the water can warm up. And here, for instance, this is in 2007, the water north of Siberia warmed up to about 5 degrees, which is incredibly warm by Arctic standards. So you're warming up the water is warming up the seabed, and the seabed has got offshore permafrost in it. Your permafrost on land extends some way out to sea, and so you have seabed permafrost, which now is melting because you've got all this warm water in the summer. So suddenly you're melting the permafrost and you're releasing what was in their sediments there, which is methane. So this is the reason why this is happening. And we found this kind of doing measurements with moorings to measure the temperature. And this is what was seen. This is an echo sounder image of methane plumes. This is the East Siberian Sea seabed, only 70 metres deep. This is an echo sounder looking sideways, seeing these huge bursts of methane gas coming out of the seabed and rising to the surface. So you're getting these huge emissions, and this is because the methane under the seabed here, where it was held down by frozen sediment, it was in the form of methane hydrates, this is what methane hydrate looks like. It looks like ice, but it burns. I mean, you could, if you put a match against this, it would burn, because it's methane molecules in a kind of little cage of water molecules, and so this was dredged up, but this is what it looks like in the sediment. But as soon as you release the pressure, these methane hydrates disintegrate and it comes up as methane gas. And here's some photos that this Russian group took of methane bubbles coming up. Here there's a thin skim of ice on the surface, so the methane is flattening itself against the ice. Here's looking from underneath with an underwater vehicle. You see the methane bubbles up against the ice. And here we look straight up at the bottom of the ice and seeing methane bubbles. So there's methane. And here's looking sideways. This is because there's climate modelers who still don't believe there's methane coming out of the Arctic, but you just have to go there and there's methane. So what's that doing? I mean, the fear, the Russian prediction is that if all the methane hydrates disintegrate as those sediments thaw out, then it will produce a kind of burp of methane, which will have a really big climatic effect very quickly, because methane is a very powerful greenhouse gas. It exists in the atmosphere for about 7 years before it gets oxidised, whereas carbon dioxide exists for about 100 years or so. So it's a quick effect, but while it's there, it's at least 20 times as powerful as carbon dioxide. So a methane burp from all this methane coming out would have an immediate short-term impact on climate, and the estimate is it might produce 0.6 of a degree of warming in 10 years, which is much far higher rate than the rest of the planet's having. So it will give us a real push to global warming just when we don't really want it. And the question is it happening already? And this are the methane levels measured by surface and satellites, and it seemed to flatten off in the year 2000, and nobody quite knows why, but maybe it's probably because one of the sources is leakage of natural gas from Russian gas pipelines, and they got a bit more careful about repairing breaks in their gas pipelines because it wasn't a good idea to look for the gas. So the methane level flattened off, but then various stations started to see an increase again from 2006 onwards. And this is beginning to be seen in satellite imaging. These are methane levels at 600 hectopascals. That's halfway up in the atmosphere. And you can see how in the Arctic the methane level has gone up since 2008. And this is, for the planet as a whole, the methane level has gone up, and you can see that it's highest in the Arctic. The methane, of course, circulates in the atmosphere, and you'd expect it to get to be the same level everywhere. But if there's a source in the Arctic, then you'll have higher levels in the Arctic. And it does look as if there are sources in the Arctic. But there's a lot of argument as to whether that's the offshore methane, or is it methane in tundra, or is it Russian natural gas pipelines, or what. But certainly the source of the extra methane seems to be in the high northern latitudes. So we did this calculation in a paper in Nature where we looked at what would happen, and we found this 0.6 of a degree of warming in the first few years after methane. And the cost was enormous. We had an economist who calculated cost using the Stern model, which is the model that was used for the Stern report, and found something like $60 trillion, which of course produced a big headline. But of course that's not a lot by standards of printing money these days. Anyway, these were the recent work which extended. So it wasn't just the Russians, because as long as it was the Russians, they could pretend that it wasn't true because it was Russians. And also, it was a woman who was leading the group, so therefore, two reasons why it can't be true. But in fact, it's been validated by Swedes, so now everybody believes it's true. So, this is it. Then there's permafrost on land is also contributing to the loss, to the increase in methane, and this is a nice place if you want to visit. It's called Dead Horse. It's a place. It's the place from which the Prudhoe Bay oil field is based. Its population is 1, which is the person who keeps the Arctic equipment store there. So he's I think he's mayor as well as chief. But Dead Horse has got this. Everywhere you go, the permafrost on land is rising in temperature. So you're going to get you're still going to get a methane burp, but it's a slower one. But in the end, there's going to be more of it coming out because a huge area of permafrost on land compared to this offshore. So these are the offshore methane is a big one. Then there's the weather, which of course everybody now is worried about, which is the fact that the jet stream has changed its position and shape. And the reason is that the jet stream is the boundary between polar air masses and the subtropical air masses, and the temperature difference between the subtropical regions and the Arctic has gone down because the Arctic's warmed up faster than the lower latitudes. So the force that drives the jet stream is less because the temperature difference being less. So the jet stream has slowed down, and when it slows down, it goes into bigger loops, and the loops move more slowly as well. So typically the jet stream is like this with lobes, so if you get in a plane and you head east, you go on the jet stream, it takes you quicker to Europe. But as with this temperature difference being decreased, the jet stream is going more slowly and bigger lobes, so you're getting Arctic air masses coming down into places like eastern United States and Europe, and then tropical air masses going up into places like western United States. So there's places where cold air is occurring now, extreme cold air in winter where it never used to be, and extreme warm air in winter where it never used to be, and staying in place because the lobes are moving very, very slowly instead of moving very rapidly. So more or less staying in the same places. So these disturbances to weather have happened for the last 6 years, so it's looking like it's a change in climate, and the jet stream will always now be slower and with these big lobes. And the trouble is, the big lobes are now taking disturbed air, either extremely hot or extremely cold, into the most productive regions for crops, which are the mid-latitude of the northern hemisphere. So that's these regions here are the most productive croplands in the world, and these are the very places that are being affected by the jet stream. And if you look at what temperature change does to crops, a lot of people say complacently, well, you know, it's warmed up, things will grow better. But that's true for some crops up to a warming of about 1 to 2 degrees, you get an increased yield, but then you get a decreased yield beyond that. And these are different crops that, in some, like Indian wheat and maize in India and Africa, you'll get a decrease, whatever the warming, but soybean in the US and maize, you'll get an increase in yield up to about 1.5 degrees of warming, and then a decrease. So this global warming is going to produce a real effect on food production, both the extreme events and the general warming reducing, once it gets beyond 2 degrees, reducing yields. And of course this is happening just when the global population is increasing really fast. Then another effect is an increase in drought, and of course there's been a lot of work done in archaeology on drought conditions that may have produced the ends of certain civilizations, like the classic Mayan. But drought is what is now becoming a norm in places like California, and the Midwest of the United States is more or less in permanent drought now. So drought is becoming a much more prevalent condition in various parts of the world which are important for food production. So the result of all that is that this is the global food price index. So the Food and Agriculture Organization worked out, you take a basket of food eaten by all the people of the world, average it all together, and look at what the price is, and what people have to pay to eat. And this index, which is already corrected for inflation, has been steadily increasing this century. And there was a big, and you can see that where it shows a big peak, because there were some particularly bad years in around 2008, you had extreme unrest in a lot of different countries, and you had famine. But even where you didn't have famine with people actually dying, you had extreme unrest because people couldn't afford to buy food. And it had another peak in 2011, and you can see that one of the causes of the Arab Spring, for instance, which started in Tunisia with a fruit seller committing suicide. There was enormous unrest because the urban young people who were dependent on having to buy food because they weren't growing it, they were getting jobs in the city and having to buy food, couldn't afford to buy food. So the riots that happened were to some extent driven by this food price index. So these were the countries which had a lot of unrest because of the food price index being high. Now since then, the FAO hasn't released food price indices recently. I think they're sort of frightened, but people who've done analysis see that it went down a bit and then now it's going up again. So the trend is upwards, and that's producing extreme hardship, but also unrest. I mean, all of the, a lot of the kind of chaos in the Middle East started because of riots based on food prices, and this can only get worse. So the final good thing for Britain is something going on in the Atlantic, which is slowing global warming for us, which is a weakening of the thermohaline circulation. That's a very slow circulation, not caused by the wind, but by differences in temperature and evaporation. And you have a very slow circulation at the surface and at depth. It takes about 1,000 years for water to do a circuit of the Earth in that circulation. But one of the places which is critical for that is a region in the Greenland Sea, not that far from us, northwest of us, where there's an ice tongue which used to grow in winter very rapidly. Ice would form. This is East Greenland Current. Ice would come round, form in this ice tongue, and the salt that was rejected into the ocean made the water sink, and the surface water sank in these extraordinary features called chimneys, which we spent a few years studying in the winter. It's surface water sinking down into the deep ocean, and over a very narrow area, like a rotate. It's like like someone opened a plug hole of a bath. Going down. So that stopped happening because the ice has stopped forming in that area because of global warming, and so we're not getting these chimneys anymore. So that circulation of the ocean is decreased, which is sometimes called the global conveyor belt. But sprockets can come off the global conveyor belt, and you're getting less circulation due to that. And one of the things about that circulation was it was bringing warm water in from the tropical Atlantic to northwest Europe. It was adding to the Gulf Stream, which is wind driven, but this was driven by this ice formation. So we're getting a lesser amount of heat being transported up here by ocean currents, and so that's cooling Britain and northwest Europe. But so the predictions for the rest of this century, it's not actually cooling it, it's warming more slowly, because there was a famous film which was absolutely terrible, useless, called The Day After Tomorrow. It showed all this happening instantly. In 2 days, New York was frozen. But it's actually happened over hundreds of years. But it does slow down the rate of warming. So the predictions are that Britain and Ireland and Iceland and the Norwegian coast of Western Europe will only warm by between 2 and 3 degrees by the end of the century, while the rest of Europe will be warming by 4 degrees plus, which is really catastrophic. I think places like Italy are going to become like North Africa. But we warm more slowly, so we're sort of okay. But of course, it's at the cost of the tropical Atlantic, because less warm water being transported up into northern latitudes means that warm water is staying at the surface down in the Gulf of Mexico and tropical Atlantic, which means more hurricanes and more severe hurricanes in the Caribbean, because the Caribbean, the water is warming. It's not coming up here and cooling us down and warming us up. It's not coming up here, so we're cooling down a bit. So that's sort of good news for Britain, I suppose. But it's not any good news for the world as a whole, because that's just the way the heat is distributed. Means that we get less heat and the Caribbean gets more heat, but the amount of heat is the same. So that's the bad news. So we're going to get continued warming even if we stopped emitting carbon, because of the fact that it takes time for the world to realise the amount of heat that's being produced by the carbon dioxide emissions. So it's what's called realised global warming, is only about 50% of what will happen in 50 to 100 years, and much less than what would happen in 1,000 years. So we're stuck with a lot of carbon, a lot of warming still to come because we've put so much CO2 into the atmosphere and it stays around for so long. We can't, if we make a terrible mistake with methane and we get a big methane burp, it will be terrible for a decade or two, and then it goes away, it oxidizes. But CO2, we've had it. You know, all this burning of fossil fuels, we're stuck with this CO2 in the atmosphere and in the climate system, and it's not going to go away, and unless we can get rid of it. And so we'll get about 4 degrees warming by the end of the century, which would be pretty catastrophic for civilization, food production. It's going to be higher still for high latitudes. It's going to produce sea level rise and drought in tropical regions, and then with this possible methane boost. So what can we do? We can. The only well, apart from switching to renewables, which is, and it's really too late to do that because we've put so much CO2 into the atmosphere. What people are talking about is geoengineering. So here's geoengineering idea that we've got to get rid of carbon, or we've got to stop the effect that it's having on the atmosphere. We can't depend on our restraint in emitting carbon gradually slowing us down. It won't happen. And anyway, because we can't restrain ourselves from driving cars. And in any case, it's too late because we've put so much CO2 into the atmosphere. So one idea is to put powder as aerosols into the upper atmosphere, which will reflect solar radiation and reduce and increase the world's albedo and reduce global warming that way. Another way, which was invented by a Scottish engineer, is to put a mist of seawater vapour into the bottom parts of clouds. So you have ships floating around with tall masts pumping up this mist into the clouds, and that whitens the clouds and makes them more reflective. So this is called cloud brightening, and it does, at least it seems to work. It looks like it would work, but you need a big fleet of ships pumping seawater mist into clouds. So you have to do something quite drastic, and these two kinds of methods would actually could slow down or stop global warming, but only if they're not doing anything about the CO2. It's like a sticking plaster. It will deal with the effects of global warming, but it doesn't deal with the CO2 itself. So the things that CO2 does, other than warming, will carry on happening, like acidification of the ocean, for instance, which is very serious. But it's better than nothing. So people are talking seriously about geoengineering, but they shouldn't just be talking, they should be doing it, basically, I think. Then the other way, which nobody's invented yet, is directly taking carbon out of the atmosphere. So you're having some amazing machine yet to be invented, where you have air coming in one side, and something inside that machine takes the carbon dioxide out and puts it somewhere else, or turns it into something else. Nobody's invented anything like that works at less than gigantic costs. So that would be something to do a kind of crash research on. Nobody is, but geoengineering is the next best thing, and I think that's our best hope, because I don't see. I think we've put too much CO2 into the atmosphere now to be able to get. We can't make this 2-degree thing that politicians are trying to get to with the Paris talks, because we've already got 2 degrees at least. We've got 1 degree, and we'll get up to 2 degrees even if we don't add any more CO2. So we're at 2 degrees already. We're going up to 4 degrees. which will be really catastrophic. So I don't see that we can reduce our CO2 emissions and get to anything that will be sustainable. So I think we have to go to something like geoengineering. So, okay.
Perfect. Thank you very much for your talk, which was really, really good. I very much appreciated it. But one element which surprised me was that you were so negative about the possibility of carbon capture and storage. I attended a lecture by the CEO of Saskatchewan down at Imperial College about 6 months to 9 months ago. And he said, it's not a complex science. He said, we have a plant which is working, and it is, depending upon the oil price, it's making money, but at times it goes below. Basically, he explained that in Saskatchewan, the only way in which they can mine their coal, on which a large number of jobs depend, is by pumping the CO2, which would otherwise be produced from the power stations, back into oil wells and using them to create it, and also to stop it up. And he said, it isn't rocket science. He said, it's a chemical plant. He said the world would actually need something like 2,000 of these plants to capture all the CO2 that needed to be captured. Whether that's correct or not, I don't know. But his argument was that it was, it is a chemical plant in the same way as you have chemical plants to crack oil and so on. And it's perfectly buildable as long as the will is there. But and in certain parts of the world, it would be ideal because, for example, where you've got oil wells or gas wells, like the UK has, for example. So we would actually be in a very good position to use this technology. But he said it's not rocket science. It's a non-costable plant. You build your power station, you build your plant, and the one takes the CO2 out of it. And it produces very high quality CO2, which can then be used as a feedstock for the chemical industry, as well as using it to push. So I was surprised that you were so dismissive of it, because as far as he was concerned, it was a working plant which is perfectly feasible.
Yes, well, I've looked at that. I'm not negative. I'm just pessimistic, because the geoengineering can be done quickly and easily and at relatively low cost, a few billions. But the carbon capture and storage is a much bigger enterprise. I mean, I think that the Saskatchewan one, a lot of it is designed for a coal-fired power station.
Yes.
So the trouble is, you can take you can have every coal-fired power station can have carbon capture and storage to get rid of the CO2 from the coal-fired the exhaust, but that doesn't do anything about all the other sources of carbon emissions: cars, aircraft, heating, everything else is. You need other ways of getting rid of the carbon. So, and then where you put it is another problem. You can put it in oil wells or where you've got oil wells, but the problem is you really have to have some chemistry to convert it into something else, because in most of the world there aren't enough places to put CO2. You have to have you have to actually have some chemistry to turn it into something else. And
well, we don't even know what to do with nuclear waste, which is compared to CO2 nothing.
So it's
imagine capturing gas.
I think that there's this scaling problem, and I've seen there's a couple of these sort of very optimistic things which when you look at in practice, it would be very difficult to scale them up to global scale. There are other more natural solutions being proposed, like biochar, which is a sort of pyrolysis of carbon waste, where you kind of distill it and you get some kind of charcoal type which you spread on fields, and then there's a liquid which you can use for something else. There's a whole load of biochar. There's kind of a biochar religion almost around, which it could well be very useful. But again, the scaling problem is I think that the scaling problem is the difficulty, and the kind of brute force approach, which I think in the end you'll need, which is not just to get rid of CO2 from power station exhaust, but to get rid of it out of the normal atmosphere. You know, have some device which is sucking in air at one end and blowing out air without carbon dioxide at the other end. There are methods that will do that, but the cost is about £300 a tonne at the moment, which is far too expensive. So I think you can, if a lot of research is done, I think it will be possible to find a cheap enough way of doing it. But at the moment, these methods that are being proposed will work up to a point in certain circumstances, but we need a global system, and so that really needs a kind of Manhattan project of research, really. But we have to do that, in fact, I mean, because geoengineering will only work for a certain length of time. If you put a sticking plaster on a wound and the wound isn't healing, you end up having to do something more drastic. So I think we have to end up with a carbon removal system, but the ones that have been proposed up to now, I think, are not up to the global job. But that Saskatchewan one is quite promising, but I think it could be applied in quite a widespread way, but not sort of widespread enough to do the full global job.
I want to ask you something. You were talking about the geoengineering, maybe a stupid question because I don't really understand anything about it. But you're saying if they're going to pump either mist or aerosol, you mentioned, on the clouds to make them basically thicker and wider, does that mean that we will pretty much end up in a grey sky or white sky look?
It will be whiter than it was. Well, no, we have grey skies in England anyway.
Wouldn't matter.
We are pre-adapted.
So instead of grey skies, we'll have brighter skies, lighter grey skies.
But would it increase the amount of clouds, basically?
No, it's not. It apparently doesn't increase the amount of cloud, but it does make the existing cloud lighter in colour, brighter. And there's been quite a lot of research done on this, and the person who developed it was actually, one of the people was Stephen Salter, so there's been quite a lot of British input there. He was a wave developer. Now he's developed a system that you can have going around on ships. So that looks quite promising, and there you can do it. You can start off on a small scale with a few ships, or just having it on land stations, and then scale upwards and see if it's working. One of the problems with geoengineering is some countries will be affected badly by it, and so they'll then shout sort of foul and say we shouldn't be changing, we shouldn't be putting powder into the stratosphere because our climate's got worse, even if the rest of the world's got better. So there'll be all these kinds of squabbles going on, but somehow have to overcome that.
Yes, I was wondering if you could say something about the positive feedback effects and the way they relate to each other. Once the forests burn, particularly the Amazon, which will have maybe between 2 and 3 degrees as it gets hotter, and also the stomata of the leaves get smaller, that will raise temperature, and then you'll get the permafrost melting, and then you'll get the clathrates melting. It's often said in the literature that happens between 2 and 3 degrees. But when I talk to scientists, they're very vague about when that's going to happen and what it means. Is there a magic number at which these effects run away with themselves? And what does that mean? Does that mean we would suddenly go from 2 to 6 in a very short period of time, for example? And also, would that be completely irreversible? Because if we have sort of a prediction of 4 degrees in the year 2100, well, if when we hit 2 or 3 degrees, we catapult up to 6, what is the meaning of a figure like 4 at all? I was wondering if you could clarify, is there a magic number at which this effect runs away with itself? How extreme would it be, and would it be completely irreversible?
Yes, good question. I mean, that's something that IPCC has kind of steered clear of. I mean, that's the graphs they produce of warming by the end of the century of 4 degrees and then 8 in the Arctic. They don't anywhere in their assessment say what 4 degrees global worldwide warming is going to do. But when you look in detail at what goes on, even with the fact that we've had 1 degree, and there's going to be some of these tipping points where you get into a whole new situation which will accelerate the warming. Like the case we've had or having is the sea ice, and it's because the sea ice is retreat because of only 1 degree of warming, but it's two in the Arctic, that the sea ice is retreating in summer and the open water is warming, and that is in itself enough to increase the melt rate of the Greenland ice sheet, increase the rate of sea level rise, but also increase the probability of having this methane burp, which wouldn't have happened before the sea ice retreated. So the sea ice retreat creates a whole new global situation where something different can happen that wasn't allowed to happen before. And we don't know what other effects like that are going to happen. Like this Amazon, that rainforest that you mentioned, I think it was Peter Cox did an analysis there where he's worked on this and reckons that apart from the fact we're cutting it down at a rapid rate, which is not good, it also, the drying out, this increasing drought at low latitudes is going to get rid of about 2/3 of it during this coming century, and that will increase effectively increase the amount of CO2 forcing in the atmosphere, because you're doing away with something that gets rid of CO2 and produces oxygen. So you could say that at a certain point, if you analyse the Amazon, so if you're an Amazon expert, you'll be able to say when the temperature rise reaches 3 degrees or 4 degrees, the Amazon rainforest will vanish rapidly, and that will then produce feedbacks which will increase the warming rate even more. But you have to, what you need is all the specialists who are looking at particular effects. I mean, I look at Arctic ice, but you should have specialists who are looking at every area of the world where a certain change leads to other changes that accelerate the effects, and put them all together. And I do suspect there's going to be some point at which you'll get an acceleration through from and it might start when the warming reaches 2 or even just 2 or 3 degrees. These extra effects might come in and that propel you quickly up to 5 or 6 degrees. So we don't know, and nobody has really said, although there's probably enough data to be able to make that prediction or that statement, but nobody's kind of dared to say it because it looks too frightening.
So is there any scientist anywhere who's actually said, well, I'll put my neck on the line and say, well, at 2.5 degrees or 3 degrees C, there will be a runaway effect? I mean, somebody was saying, some scientists were saying to me, I think it was in the Permian, that temperatures rose globally 7 degrees C in 10 years.
Yeah, well, I don't think anybody's put their neck on the line there, but one person who has, as far as sea level rise is concerned, is James Hansen, who's he's always been pretty outspoken and has about climate change and knows his stuff. But he's said that these predictions of less than a metre are completely wrong, and he's reckoning 5 metres of sea level rise by the end of the century, and that would be catastrophic because the whole of, I mean, the predictions are of existing changes in sea level are that might produce an economic collapse. Say in the US, for instance, there's such a huge fraction of the US economy is just real estate prices in coastal cities, and it's apparently massive because all the most expensive real estate is on the coast. You drown the coast, you're actually really drastically affecting the economy. And there's a very nice American book out recently called High Tide on Main Street, which they analyse this and conclude that apart from the fact that cities will disappear, like Miami and New Orleans and the Boston and so on, that the economic effect before that will be catastrophic. So if that's what will happen with a metre, but if you have 5 metres, it's really catastrophic. So Hansen is predicting 5 metres based on how fast the Greenland and Antarctic ice sheets are disintegrating. So he's put his neck on the line there. Luckily he's retired, so they can't threaten his career anymore. But some scientists who know what they're talking about are coming out with some quite extreme predictions.
It sounds like the developed nations or the first world is much more vulnerable than many other places simply because they wouldn't even know how to plant a piece of maize and keep it alive. I mean, if disaster happens, you could go back to hunt and gathering, but you have to know the technical skills to be able to take advantage of whatever's left. There is no. But now, I mean, outside Tesco's, they wouldn't know how to get anything.
We've got more to lose, yeah, but on the other hand, it's crowded countries like Bangladesh. You know, they're low-lying, they're going to have a big increase in flooding and storm surges, you know, regularly going to be killing 100,000, 200,000. That's the sort of thing that happens quite often, and it appears on page 10 of the newspaper, 100,000 dead in Bangladesh. But it will happen more frequently, and they haven't got anywhere to go because I think there's something like 20 million people live less than 2 metres above sea level, and they can't go back. They can't go back inland because there's another 20 million people behind them saying, clear off, there's no land. And so it's catastrophic for crowded, poor countries that are low-lying. That would be really bad.
Sounds very Malthusian, all this. I mean,
Can I ask you a brief question from your area, particular area of expertise? The polar regions, if you actually get large quantities of ships going through the Northwest Passage at all times in the year, presumably that would have an impact upon the breakup of the sea ice and so on. Do you think that would be a substantial effect, or would it just be fairly minor?
No, it would be minor. I think people have looked at that, and it's minor. Something a bit less minor would be the black carbon produced by but now they're insisting that any ships using the Arctic have to have very clean fuel.
like the Volkswagen.
Yes. They really have engines produced by Volkswagen.